Hi, my name is Siva and I will be presenting V2VNet, vehicle-to-vehicle communication for joint perception and prediction. A core component of self-driving is perceiving the world and identifying the actors in the scene, such as vehicles, pedestrians, or cyclists, and then forecasting their future motion. We call these tasks perception and prediction, or PNP. Significant improvements have been made with deep learning and 3D point cloud processing to leverage LiDAR sensor data to have good PNP, but issues remain. For example, PNP suffers from low visibility in faraway areas and occluded regions due to limited sensor data as compared to nearby and unoccluded vehicles. Model improvements and training techniques can only go so far to improve PNP when there's little or no evidence. We therefore pursue another direction to improving PNP, vehicle-to-vehicle communication, or V2V, which allows a fleet of vehicles to cooperatively view the world from multiple viewpoints and communicate what they see with each other. Thereby, they are able to see through occlusions and thus see further. To leverage V2V to improve the perception and prediction system for self-driving, we first need to decide what information to share between vehicles. Two options immediately come to mind: transmitting the input LiDAR sensor data or transmitting perception and prediction outputs. When we transmit input sensor data, we gain the benefits of no information loss. Each self-driving vehicle, or SDV, has access to the same information seen by the other vehicles. However, sensor data is large in size, and the more sensors there are on the vehicle, the more information there is to be sent, making this approach not scalable. Our second option is to transmit the outputs of perception and prediction. The main advantage is that the messages will be very compact, as describing bounding boxes and trajectories requires few parameters compared to LiDAR inputs. However, only transmitting outputs discards scene context and actors' properties other than the position and velocity that may be useful for PNP reasoning. To achieve the best balance of small message size and improved performance, we propose transmitting intermediate representations of the neural networks that are performing joint perception and prediction. This gives us the best trade-off, as the intermediate representations are typically compact since they are highly compressible while still containing information about the scene context. Also, their expressiveness is not limited as with output representations. And moreover, using intermediate features leverages distributed computation for multiple vehicles, as each vehicle first processes their own sensor data. But how do we intelligently combine these intermediate representations to improve perception and prediction? We propose V2VNet, the first sophisticated AI-based V2V approach which aggregates intermediate features with a graph neural network. First, sensory inputs are encoded into a compact intermediate representation, which is then compressed and broadcasted to other nearby vehicles. Then, messages from other vehicles are received and decompressed, and all features are aggregated with a spatially aware graph neural network. Finally, the aggregated features are processed to generate perception and prediction outputs. The key component of our method is a spatially aware graph neural network, which intelligently combines observations from multiple views seen at different points in time. We will now discuss this component in more detail. First, each vehicle receives intermediate features in bird's eye view, along with the timestamp of the message and the relative pose of the nearby senders. Including the timestamp and relative pose is important, as the V2V involves asynchronous vehicle communication, and the vehicle relative pose provides insight into which areas are viewed by each SDV. Next, we concatenate the time delay to the message features and use a CNN to learn to compensate for messages with a delayed timestamp. The time delay is easily accessible, as all vehicles have access to a global clock. After time delay compensation, the messages are aggregated by the graph neural network. At each message passing stage, the feature maps are warped into the same coordinate frame of the receiving node, and features inside the region of interest are used for accumulation. The GNN intelligently aggregates intermediate representations in a spatially aware manner. When it comes to evaluating V2V methods, there is a lack of suitable real-world datasets. Existing V2V datasets are created in a platoon or convoy setting, where cars closely follow one another, as can be seen on the right. Observations captured in this setting are highly correlated and therefore fail to capture the diverse V2V scenarios that will occur in practice. For example, in the convoy setting, we will never see SDVs approaching from the opposite direction. To address this lack of benchmarks, we created V2V Sim, a large-scale V2V dataset using our new high-fidelity LiDAR simulator, which faithfully replicates the real-world LiDAR scans. In this dataset, we take the 3D reconstructions of logs and real-world LiDAR sweeps and simulate them from the viewpoints of the other vehicles in the scene. Then, all the other vehicles can act as if they were SDVs. By doing so, our SDV topologies directly correspond to real-world traffic scenarios. Here you can see an example of a V2V Sim scenario. With this constructed virtual world, we can now simulate realistic LiDAR from different vehicle viewpoints, as shown in the right. Each colored autonomous vehicle has a corresponding colored LiDAR point cloud generated. We allow up to 7 SDVs in each frame. Here are the quantitative results. Average precision measures detection performance, L2 error measures the error of predicted trajectories, and TCR measures the collision rate of predicted trajectories. With V2VNet, we reduced the perception rate by over 68% when compared to single vehicle, no fusion performance, as shown in the first row. Furthermore, V2VNet achieves superior performance to both the input LiDAR fusion baseline and output bounding box and trajectory fusion baseline. As mentioned earlier, transmitting intermediate representations allows for highly compressible message sizes. By incorporating valet compression, V2VNet achieves the best trade-off between message size and performance on both perception and prediction metrics. At 10 Hz, our method only requires 0.2 megabytes per second during communication, which is easily satisfied as the cheapest dedicated short-range communication hardware provides more than 3 megabytes per second. V2V performance in perception and prediction tasks also increases with the number of vehicles in the network. As the density of SDVs increases in the real world, V2V communication will become even more effective. V2V also provides dramatic improvements on far away and occluded vehicles, as shown in the top row of the figure, since there is a significant lack of LiDAR evidence in these particular cases. Furthermore, V2VNet is particularly effective at detecting vehicles with high speed, as shown in the bottom row, beating LiDAR and output fusion by a large margin. High-speed vehicles are often difficult to handle due to motion blur and rolling shutter. These effects are due to the fact that since the vehicles are moving, the LiDAR observations become warped, like the camera image on the left, making it difficult to predict where the object is at a specific point in time. The previous experiments assume perfect localization of the SDVs, as we need the relative poses to transform messages into a shared coordinate system. But in the real world, there may be localization errors. We evaluate the performance when we add noise to the estimated position and heading of each SDV, as shown in the left and right column of the figure respectively. Unlike other fusion methods, V2VNet is more robust to localization errors, as leveraging a GNN allows us to intelligently aggregate the messages and be more robust to this error. Furthermore, in the real world, we cannot always expect messages to arrive with perfect timestamps. It's important that V2V communication is robust to delayed messages. Here, our proposed V2VNet is much more robust than the other fusion alternatives. In this evaluation, we account for time delay in output fusion by extrapolating vehicle trajectories, and no compensation is done for LiDAR fusion, as extrapolating LiDAR point clouds is non-trivial. We now show some qualitative results. The ground truth is in red, the V2V outputs are depicted in green, and the single vehicle outputs are in blue. Here's an example where we showcase a significantly higher recall of V2VNet. Notice the green boxes where the V2VNet detects vehicles that are missed in the single vehicle case. And here, V2VNet can detect a high-speed vehicle behind, and thus wait before performing a lane change. And finally, here is a qualitative video demonstration of V2VNet. We show on top the vehicle configuration, and on the bottom, the output perception and prediction with V2VNet compared to the ground truth. V2VNet pushes the perception and prediction performance even further, allowing for even higher operating speeds while simultaneously providing safer and more comfortable driving. In conclusion, we introduced V2V communication for joint perception and prediction. We then presented V2VNet to transmit and combine intermediate PNP representations intelligently to get the best performance and compact message size. We then demonstrated on a realistic V2V Sim dataset that V2VNet has promising improvements over the single vehicle method. For more details and results, please check out our paper. Thank you.